Hello, calculus people. Hope you're having an amazing day today. Uh, Today we're going to be talking about what integrals are really used for, and that is to find areas under curves. Now, the only difference between what we've done so far with integrals and today we're actually not going to use them. And I'm going to go through and I'm going to explain to you really where the idea of the area under a curve came from with an idea called a Riemann sum. And you'll see about that in a little bit here, a Riemann sum. So first, let's kind of identify the basics behind area under a curve. Let me go in here a little bit. We've got a pretty simple graph right here. It says use 4 rectangles to find 2 approximations of the area of the region lying between the graph of f of x equals x squared and the x-axis between 0 and 1. Okay, so a couple of things. First off, they gave me an equation. It looks like the right-hand side of a parabola here of the parent function. F of x is x squared. And what they're wanting me to do here is from 0 to 1, they want me to bust this thing up by dividing it into 4 equal parts. Draw the inscribed rectangles using left endpoints. Inscribed means that it's going to be all underneath the curve. Alright, so a couple of things here. It's inscribed, and we are using left endpoints. So what I'm going to do here is I'm going to draw 4 rectangles starting at certain points and going up with the left side, the left endpoint touching the graph. So here's what that's going to look like. I'm using 4 rectangles here, so it's going to go from 0 to a fourth, from a fourth to a half to 3/4, and 3/4 to 1. So here's kind of what the idea of what they're wanting. Oops, something like this. I want a rectangle with the left corner right here, and I just do this to help me remind myself what's supposed to be touching. The left corner touching the graph. And I'll continue to do that. Like this. Alright. And the fourth one is, this graph isn't really that great for it, but it's under here. It goes down like this, comes across and touches. It's actually a height of 0 on that one. Okay, so really think about what's going on here. They're wanting you to find the area under the curve. That's going to be the area of these 4 rectangles. Now, as you can see here, if we were to find the area of these 4 rectangles, that would be a little under what the actual area is. See these little blank spaces right here? It's going to be a little bit under. So kind of keep that in mind here. So going back up to my problem here, it says I'm using 4 equal parts, right? I'm using 4 equal parts. So what I'm going to do here is I'm just going to come up with the area of these triangles. And the key to this is this word right here, sum. I'm going to add up all the triangle bits here. All right? So think about the formula for area of a rectangle first. The formula for area of a rectangle is base times height, right? It's base times height. Well, in this case, how big are each of my bases? Well, they're all 1/4 apiece, right? This is 1/4, or excuse me, the same base. All of your rectangles have a base of 1/4. So the area that I'm trying to look for has a base of 1/4. And the height is determined by f of x. So it's going to be 1/4 times f of x. Base times height. My base is 1/4 apiece. My height is whatever that x value is. Right? So let's kind of figure out what this is going to be here. My height over at this point, my height of this first rectangle, let's do it this way. Height equals, in this case, f of 0. I go to this x value of 0, and it's whatever that is. We'll come up with that in a second. This height right here, f of 1/4. See, if I go to 1/4 on my x values and find my graph, that'll give me my height. If I go to a half, that'll give me my height here. If I go to 3/4, that'll give me my height here. So let's talk about this here. We're going to do a left-hand sum, and there's going to be 4 parts to it. So what I'm going to end up with here, I'm going to have 1/4 times 0, that's this flat line right here, base times height. And then let's add together this one here. We've got 1/4. So f of 1/4 right here. Let's see what this is going to do here. If I was to plug 1/4 into this function, what would my height be? So let's see here. Let me do this over here. F of 1/4 is 1/4 squared, which is 1/16. So it's going to be 1/4 times a height of 1/16 plus a base of a 4th times a height of, if I plug in a half into my function, I'll get 1/4 plus 1/4 times the height of this one here, so 3/4 for my x value. I'm going to plug that into x squared, and that'll be 9/16. Alright, so a left-hand sum using 4 units. Now if you notice, they all have the same thing in common. They all have a 1/4, right? All of them share a 1/4. So let's pull that out and see what happens. We'll have 0 plus 1/16 plus a 4th plus 9/16. So that's going to end up being 1/4. 1/4 is going to be 4/16, so it looks like we've got 9/16, 4, 5, so 14/16. Alright, so again, all I'm doing here is taking base times height, base times height, base times height, base times height, but they all have in common that 1/4, their base. So if you just pull that out, all you got to do is add all the heights together. Boom, there you go. 1/4 times 14/6, so this will be, what would that be, 14/64, 7/32? Divide each of those by 2. Now, where's my calculator here? Roughly 7/32, this is going to be an estimation, so it's approximately 0.219. Now, this is telling me that this is the area of these 4 rectangles underneath the curve. But we know, since we have a little bit of extra space in here, that this is going to be an underestimate, right? Underestimate. So kind of keep that in mind. If you have extra space you haven't taken into account, you're going to have an underestimate because you have to fill in that space, right? Then repeat the process using right endpoints. So repeat the process using right endpoints. Now this one's a little bit different. See, on this one, your left endpoint came up and touched the graph here. Now what I'm going to do is I'm just going to, I'm going to raise these 4 bars up. I'm still using just 4. So I'm going to raise these 4 bars up until the right endpoint hits the graph. Here's what it'll look like. You start off with a 4th, and then 1/2, 3/4. So now instead of the left endpoint hitting on this right triangle, the right endpoint is going to hit. So I'm going to take my right hand side and go up. Oh my. So now it's going to look like that. And my right endpoint is what's hitting here. and then up to this point on the graph. All right, up to this point on the graph, up to this point on the graph. See, now this far left-hand one actually has some height to it. It's got a little bit of height. So let's see what this would actually be here. We've got an area. See if I can get all this in. There we go. Area, again, is base times height, right? Now I'm going to try and skip just a few things on here and kind of use my math skills and see where I can go. So my area, again, my base is 1/4, and my height is f of x. So let's figure out what f of x is, and this should really be in brackets here. Looks better in brackets. Everything looks better in brackets. So we're going to do a right-hand sum. We're using the right-hand points, and we're using 4 blocks. So that's going to be 1/4. And remember up top where I could just add together all of my exponents, or excuse me, not exponents, good grief. I could add together all of my heights. Like if I pull that 1/4 out, I'm going to skip this middle step, and I'm just going to come straight to here and just add up all of my heights in there. So 1/4. So again, I go, now in this case, I go to 1/4, plug it into x squared, I get 1/16. Plus 1/2 plugged into x squared, I get 1/4. 3/4 plugged into x squared, I get 9/16. 1 plugged into x squared, I get 1. So again, these 4 values right here come from this point, this point, this point, and this point. They give me your heights. So coming through, R of 4, right-hand sum, 4 blocks. It's 1/4. And that's going to be 16, 9, 4, and 1, so 30 over 16. If you change 1 into 16 over 16, change 1/4 into 4 over 16. So you got 16, 21, and 9, 30. And that's going to be roughly, let's see, that would be, take your 2 out, you get 15 over 32, which is about 0.469. And this one, if you notice here, we've got the space of all of this rectangle, right? All of this rectangle, all of this rectangle, all of this rectangle. So if you notice here, this is quite an overestimate because we've got all these 4 pieces here, right? So this one, I want you to write this down here, is going to be an overestimate. Now that could change with your function. Please don't misunderstand. Right-hand sums are not always overestimates. Left-hand sums are not always underestimates. It depends on the graph. If this was concave down, for example, it'd be the other way around. Okay, so this is just introducing the idea of what we call a Riemann sum, and that's basically what a Riemann sum is. You're taking and you are adding together the heights times the bases. So let's take a look at what it actually looks like. So Riemann sum, and it looks like Riemann, but it's Riemann sums. A Riemann sum for a function on the interval AB is a sum of the form. All right, let's talk about this form here. Here's the function, right? And what you're doing is you are going to add up this Greek letter sigma, stands for summations in math. So you're going to add up all of your f of xi. This is your heights. This is your height. F of x, that gives you the height of your function. And delta x is the base width change in x. It's how much your base width is changing. base width change in x. So it's just how much is your base, or how big is your base, right? N is the number of intervals. So with this one here, with this particular example, we have 2 intervals. I'm doing 2 sums right here. So it's going to be 2 intervals for this one. And what I'm going to do is just kind of use this as an example for all of these. So delta x is going to be the width of each interval determined by this guy right here. All right? So again, delta x is your width. Now n, this guy up here, is the number of intervals you have. I equals 1, that just means you start your summation at 1 and you go to 2. If you just had 1 interval, then n would be 1. Not much to change there. So again, delta x is found by this guy. So let me just throw out some numbers here. Let's say that this is 2 and this is 4. Right? So delta x then, if you use this guy right here, 4 minus 2 over, how many am I using? 2 intervals, so 2. That means that each base is only 1 unit wide. So this will be 2, 3, and 4. So each base is only 1 unit wide. So again, you take your right-hand side, subtract your left-hand side to find out how wide it is, divide it by n number of intervals, and that tells you how wide each interval is. F of xi, it's the length. You could also think of it as the height. I like to think of it as the height, personally, of each interval determined by the value of the function. So if a function is increasing, which is the largest, the left or the right sum? Well, here's an increasing function. Which one would be larger, the left or the right? This is the same function we had earlier. If it's increasing, then the largest sum is going to be the right-hand one. See how this right hand goes up and touches here, and we've got all this extra space right up in here? This extra space makes it an overestimate. So in this case, the right-hand sum is the largest. Now, if your function is decreasing, it's going to look something like this. Let me do it over here. Let's say a function is decreasing. Which one would be the largest, left or right? Well, the right-hand sum would come down like this, with the right-hand points touching. So I would have an underestimate. So in this case, the left-hand sum, where the left-hand points are touching, is going to be the largest. And that kind of goes back to the whole, what I said on the front page about concave up, concave down. This is just telling you that the largest sum is not always the right. It can be the left-hand sum. Now, the best type of sum is going to be what we call the midpoint value. And that's for a few reasons. The midpoint value sum, this is a better estimate. And that's mainly because the height of the rectangles is in the middle. I want you to write that down too. The height of the rectangles is in the middle. So the reason why this is a better estimate here, let me zoom in, you've got some overestimate right here, you've got some underestimate right here. So this is going to be your best bet at getting a really accurate area. Okay, and we're going to do a lot with Riemann sums. Today is just really an introduction. So let's try a couple of problems very, very quickly. Pull back. There we go. So example here. Sketch a graph. Calculate the left, right, and midpoint Riemann sum. So first, let's sketch a graph. 1 over x. Now, if you remember, 1 over x has vertical asymptote at 0, horizontal asymptote at 0 since it's bottom heavy. It's going to look something like this. It has origin symmetry. It's going to look something like that. And what we're doing is finding the Riemann sum between 1 and 2, where n is 2. Again, this n equals 2 means 2 rectangles. So let's call this 1. We'll call this 2. And first, I'm going to find a left Riemann sum. So let's go ahead and draw it, see what it looks like. I know I'm going to have 2 rectangles here. Alright, so this is what it's going to look like here. That's a left-hand sum. And let's figure out what's going on here. So my delta x, how wide is each rectangle? Alright, you probably don't need the formula for this, but I want to show you how to do it just in case. How wide is each rectangle? Well, each rectangle goes from 2 to 1. So 2 minus 1 divided by 2. 2 minus 1 divided by 2. And that's 1/2. Alright, so the left-hand sum, we're going to do a left-hand sum using 2 rectangles, is 1/2. This is your delta x right here. Times f of 1. I'm going to need f of 1 right here where it's touching the graph. Plus, looks like f of 3/2. Now, if you're only using 2 rectangles, then you only need 2 heights. Make sure that you keep that straight. Alright? So, this is going to be 1/2. And if you plug a 1 in here, you get 1 over 1, which is 1. Thank goodness for that. Plus, if you plug in 3/2, you get 1 over 3/2, 1 over 3 over 2, which is 2/3. Alright, which is what? 3/3 and 2/3. It's 5/3, 5/6. Which is roughly the equivalent of 0.833, on and on and on and on. Now, is this going to be an under or over estimate? Well, since I have some extra leeway out here, since I have extra rectangle showing, it's going to be an over. I'm just going to put over out here. Alright, same function, now I'm going to do a right-hand sum. So I'm going to come down here, draw my function again. Same function, except now, from 1 to 2, I'm going to do a right-hand sum. So I'm going to start on the right with 2, go up to my graph, go over to my next rectangle, start at, this is 3/2, go up, over, and down. So now I have a right-hand sum with 2 rectangles. My delta x is 1/2. Remember, everything that I'm doing is coming off of this. So I'm going to do delta x, and I'm going to add up all of my functions. Add your functions, multiply by delta x. So it's delta x, which is 1/2. And I'm going to add up all my function values. So I need this point right here. Just go to where your rectangles touch the graphs. I need f of 3/2. And I need f of 2. And I'm going to add them up. That's a Riemann sum. So this is going to be 1/2. And we said that f of 3/2 was 2/3. If you plug a 2 into 1 over x, you get a half. Again, I'm plugging that into this guy up here. 1 over my x value is 2, which is going to be 7/12. Yeah. I think 7/12, which is roughly 0.583. And see how all of my rectangles are under my graph? That's going to be an underestimate. And then you have a midpoint. Now the midpoint sum here, I'm still going from 1 to 2. Let's graph our picture again. Graph our function, our picture of function. Okay, I'm still going from 1 to 2, right? Except now the height is going to be in the middle of the graph. So my rectangles are still going to start in all the same places. The only question is, where do they stop? So I'm going to go up to the middle of these numbers, find my graph. There's my height. Go to the middle of 3/2 and 2, find your graph. There's your height. All right, so you can definitely see how this one is going to be the best type of estimation. So you've got a midpoint sum, 2 rectangles. Your delta x is still the same. It's still 1/2. What's going to change now, though, are your functions. So what's halfway between 1 and 1.5? Well, it'd be 1 1/4, right? 5/4. Plus, what is halfway between 1.5 and 2? It'll be 1 3/4, 7/4. All right. So I'm going to go through and do this just very quickly here. This is going to be 4/5 plus 4/7, which is 475. 75 is 35 times a half. No, wait. Yeah. So let me see what that'll be here. Go away. 1/2. 4 divided by 5 plus 4 divided by 7. 24 over 35, which is roughly 0.686. And this may be an overestimate, it may be an underestimate, but we're going to talk about that at a different time. For now, this is your midpoint. Now this is, again, this is the closest estimate that we have. All right, it is the closest estimate that we have, but it's still a little bit off, and we'll talk about which one it's going to be at a different time.